In this video, we are going to design and analyze a dipole antenna. So, a simple dipole antenna consists of two cylindrical metallic rods. So, when you are going to design, please ensure you assign the material to be a conductor like a copper or PEC, perfect electric conductor. You can choose whatever it is. Right? Ensure that you select the material as a conductor. So here we are going to take a random frequency at around 15 gigahertz. Right. So whatever is your design frequency, you take that as uh, f value, and we'll have to substitute in the wavelength expression. So wavelength is going to be lambda naught, which is c by f. So c is 3 to the power 10, 3 times 10 to the power 8. Upon the frequency, we'll get it as for 15 gigahertz frequency, we are getting it as around 20 millimeters. So one wavelength is of 20 millimeters, but a typical dipole antenna would have an approximate length of half the wavelength. So lambda naught by 2, approximately, again please note it's going to be an approximate value. So we'll have to fine tune it later on, that we'll see in the simulation as well. So the approximate length will be around 10 millimeters. So overall length is L value is 10 millimeters. So approximate length of each rod would be approximately L by 2, which is lambda naught by 4 or quarter wave length. So in this case, it is coming out to be 5 millimeters. Right. So we'll tune this L value for obtaining per our dipole's performance at 15 gigahertz. Right. Now our design consideration, again taking the frequency as 15 gigahertz and its corresponding wavelength as 0.02 millimeter. So the gap of separation of the two metallic rods, we would assign it as 1/100th of the wavelength. In this case, it is going to be 0.2 millimeters, and the radius of the rod also will be taken as approximately lambda naught by 100. So you can take whatever is the realistic value that you wish to take, but we can, for simulation purpose, we'll take it as 1/100th of the wavelength, which is in this case for 15 gigahertz, it is 0.2 millimeters of gap, and the radius also. So the simulation setup, what we would consider is center frequency at 15 gigahertz, simulating frequency range just for analysis purpose. Again, at all instances, we will not go for this wide range of frequencies, but just for studying purpose or first time simulation purpose, I am taking it as f naught by 2. That means half the center frequency to twice the center frequency. So that would be the frequency range that we would be considering in this case. Since f naught is 15 gigahertz, half the frequency is center frequency is 7.5 gigahertz, and twice the center frequency is 30 gigahertz. So we'll give this as the simulation range. Now we would be plotting the S11 in dB scale, and S11 should be less than minus 10 dB. Basically, whatever power that you give to the antenna, how much is being reflected back, right? So if minus 10 dB is a reference point, so what we mean is only 1/10 of the power that we give is reflected back, meaning 90% of the power that we are giving at port 1 gets coupled to the antenna. Right? That's what minus 10 dB signifies. Right? So we would mark the frequency points F1 and F2 at which we get the S11 is between which we get the S11 as less than minus 10 dB, and the F2 minus F1 will give us the bandwidth. So I'll explain this in the simulation as well. You can always find the percentage bandwidth F2 minus F1 by F0, F0 being the center frequency, and plot the 3 dB gain at your design frequency F0. Here in this case we have 15 gigahertz. So this is the overall simulation setup that we need to look into it. So let's open Ansys Electronics Desktop. So once you open Ansys Electronics Desktop, you'll have to create a new project. So click create new project. So go to HFSS and select this HFSS value either over here, or you can always go to project and insert HFSS design. So that HFSS design is listed under this section. So let me save this project. So for now, I'm going to save it as such. So you can give whatever name it is and note down the location where you are saving, right? Okay, so in our design, we had just seen that only three variables we would be considering. One is L, the length of the rod, right, which is half the wavelength, and you know L by 2 will be length of each rods, right? So total length will be L for the dipole antenna. So length of each rod will be L by 2. So we'll take the L value as 10 mm and the gap of separation G as 0.2 mm and radius R as 0.2 mm. So gap is lambda naught by 100 and radius is lambda naught by 100 based on the current frequency we have taken. Right? So whatever is your design frequency, you can find out its wavelength and 1/100th of its wavelength you can give as gap of separation and the radius as well. So in simulation, let's yeah, you can select the project variables and enter it well in advance. So you can go to project and project variables. So over here we'll add the first variable as L, right? So L, it's going to have a length of 10 mm. I'm going to type mm. So automatically the unit type changes to length and units it's showing mm. So I'm clicking OK. So you can either create it as a project variable like this, or you can also go to this section over here. Uh, anyway, we'll for now create the project variables over here itself as L, and then next the radius R 0.2 mm, and the next variable is gap G as 0.2 mm. Right? All these variables are have been defined right now. So I'm just clicking OK. Now we need to create a cylinder, cylindrical rod, right? So there is a draw cylinder option available over here, right? If you click, you'll get this. You can click a draw cylinder over here, or go to draw option and select a cylinder over here. So it will give a where do you want to click? I mean where do you want to draw this? It will ask. So this is the workspace. So I'm going to click at three random places. So center of the base, at radius and height. Right, so those were the three clicks that I made. But since I have clicked at random location, so what we can do is we can always change the values. So I'm going to align it to the Z axis. So we need to select, double click at create cylinder. Right, so a vacuum cylinder has been created. Please double click over here. So center position X will be 0, Y will be 0, and along Z it's going to be gap by 2. Sorry, since there is a dollar symbol over there, so we can always give that dollar G over here. So in case if you are going to, on the go, you are giving the value over here as G by 2, right? Separately, if you give as G or G by 2, whatever it is, it will create a new variable over here. Since we have already created a variable which is dollar $G, so you can give the value as dollar $G by 2. Yeah. So the radius is going to be dollar $R and height, sorry, it should be dollar $R and height will be the variable L, sorry, L by 2, right? So half the length will be the overall dimension. So this gives us the top rod. Now we'll have another rod placed below this, right? So what we can do is we can always duplicate it. So right click over here, right? Right click and edit, duplicate, mirror, right? Right click, edit, duplicate, mirror, click mirror. So where do you want to mirror? So along x-axis you have to click at 2 points, right? So I'm clicking at the origin and just along, along z-axis I'm just clicking at 2 points. So just to check the same. go to this duplicate option under cylinder 1, double click, you will be able to see the normal position is 0, 0, 1. So you have to assign it like this, meaning we are just duplicating it along the z axis, right? Meaning xy plane will be the mirror. So at the xy plane, as a mirror, we are creating the structure. Now, in case if you want to change the dimension, what we can do is we can always go to this project variables and change the dimension over here as 8 mm or whatever is the dimension. So the structure also gets changed. You can just check the values over here. L by 2 becomes 4 mm, right? So I'm just for showing it, I'm uh, just for visualization purpose, I have just made it, but you can always resume the value. Go to project variables, and you can assign or set the value as in the previous case, right? So 0.2 mm, 10.2 and 0.2. So click OK. So now we have created two vacuum cylinders. Please ensure that those are assigned as metal. So select both the cylinders, right click, assign material, and you can assign it as a copper or a PEC, perfect electric conductor. In some videos you might have seen PEC being used. PEC means perfect electric conductor. That is the ideal metal of infinite conductivity. Right? So now we have assigned two copper cylinders over here, right? So our next step will be we need to create a port or assign a port over here, right? So just before going to that step, let's provide the solution type. Go to HFSS, select solution type, and select the model solution, right? So once you have selected it as model, so we are going to draw the port right now, right? Now just zoom in sufficiently, right? So what we are going to do is we are going to assign a port between these two. So a plane, basically from center of the bottom plane to the top plane we need to select. So for that we are going to draw a rectangle. Now in general, if you draw a rectangle, see the working plane that has been selected, the grid that you can see is oriented towards XY plane. But we want an port to be assigned along the z axis. So it should be, the working plane should be aligned to either xz plane or yz plane. So to change that, we need to go into this visibility. So the grid is there, right? So that we can select it to be xz plane or yz plane, whatever it is. So you can go out here and change the corresponding plane, right? So right now I have given it as a xz plane. So along xz plane, I'm going to draw a rectangle over here, wherein both the cylinders diameters would be connected. Right? I'm just selecting a rectangle. So starting from one corner uh, point of the first one and to the next corner point of the second rod. Right. So basically, we are trying to connect a plane over here. We select a. We are going to draw a port on this plane. So this just a reference plane. We are not going to assign anything as such right now. However, we'll use this rectangle for assigning the uh, our this port. Right. So again, what I generally tell my students is always use parametric values, right? So the radial position is first click. What we did was at $R the radius and half of g by 2. Sorry, half of g, right? Dollar right will be the was the first click point, right? Along x at radius r and along z at height g by 2 we made the first click, so that is the starting point of this rectangle. So the overall x length of this rectangle is 2 times $R, but in minus direction, right? So the radius is, from this location we move to the bottom right of this rectangle, right? So the bottom right point is at x distance of minus r by 2 and a z distance of minus g, minus $10, right? So when you click OK, so it will be assigned as parametric values. Now we need to select this rectangle and assign port. right? So for assigning port, right click, assign excitation, port, and we can give lump port for now. I repeat, select the rectangle, right? Either you can select it on the working plane, or you can select it over here where all the components are listed. So right click, assign excitation, port, and lump port. Now 50 ohm impedance is the general reference. Now click next. It will ask for the integration line. Now this integration line we need to select it as a new line. Once you click new line, so go to this, scroll to this center. So until you see a triangle, right? See, you are able to see this triangle right at the bottom. So make your first click over here and move your mouse to the top plane, and again you will see a small triangle assigned at the center of the top edge of the rectangle. So make a click over there. So right now we have defined, click next and finish, so that the rectangle will be listed under the lumped port, right? So here under the HFSS design you can see the excitation uniquely. So this port is going to be the excitation. This rectangle is going to be used as an excitation port, starting from the bottom point to the top point. Meaning, we are going to connect at these two edges and give the input to the dipole antenna. Right. So one input will be given to the top, and top rods this center, and the bottom rods this center will be the other reference line, which two cables will be connected to apply the input, right? So those two will be assigned at these 2 points. So that's what we are signifying using this lump port. Now click save. A boundary needs to be assigned, right? A simulation boundary needs to be created. So for that, what we can do is, since we are concerned about simulating our result at 15 gigahertz, and what is the highest frequency that you want to consider for simulation, that needs to be the lowest frequency, whatever is the lowest frequency that you need to consider. So that can be given as the bounding box reference dimension. So how it is done is, so right click on screen, create open region. It will ask for what is the operating frequency that you intend to work with. So since I have taken it as 15 gigahertz, I'm going to give it as 15 gigahertz over here. So whatever is your center frequency, you need to give it over here as that corresponding frequency and click OK. So it will create a box around it, wherein it is going to create an open region. So it is going to be like this antenna is going to be placed at a space where uh, you know uh, all other physical aspects are out of reach, right? So the simulation region is going to be considered like this for 15 gigahertz. So if you have selected a much lower frequency, there is a dimension may be slightly larger according to whatever frequency that you have selected, right? Now again, go to analysis. So boundary we have checked, excitation we have assigned. Now go to analysis, right click, add solution, and click advanced. So over here, the center frequency I would consider it as 15 gigahertz. Number of passes, generally I'll take anything greater than 12. So I'm just giving it as 13, or you can give 15, whatever it is. So this basically performs multiple iterations until it converges to a particular solution, right? So number of passes is not dependent on frequency. It's just a general number. So you can always give it as 12, or at least have the habit of giving it 12. So here I'm going to be concerned about only one single point of radiation pattern, which is 15 gigahertz is my interest. So if you need to design for multiple frequencies, you can always enter those frequencies in multi-frequency, so that you can see the radiation pattern at different frequencies. Now, since my design frequency, center frequency is 15 gigahertz, I am giving the single as 15 gigahertz, single option as solution frequency, and I'm clicking OK. So it is going to ask what is the range of frequencies that you wish to simulate. So as I told you earlier, center frequency was 15, so half the frequency I'm going to give it at the starting frequency, and end point I'll give it as twice the frequency. You can give 1.5 times the center frequency also. That is what we are seeing over here, right? In case if you have too much concern about is your design correct or not, if you want to see a rough estimate, so you can very well assign twice this frequency, and I'll leave it as 401 points, simulation points. So save field set basis frequency, I'll just enable it, meaning at 15 gigahertz I want the 3D plot, 3D fields to be stored. I'm clicking OK. So now all the inputs have been given. So I'll click save. Now just to check if you have given boundary correctly, excitation correctly, and the simulation setup is correct. So what we'll do is right click at the HFSS design and perform a validation check. So when you click validation check, so it will show all green tick marks. If any of these are not enabled or there is a X mark, you will have to go and check the same. See, boundary we have given, right? Radiation boundary, one open box we have created. We have assigned the boundaries and excitations. We have drawn the 3D model. All the design settings are done. Mesh operations, you don't need to worry about it. By default, Ansys will take care of the meshing part. However, on a separate note, you can look at how meshing can be done separately in YouTube or any other resources. Right? Analysis setup, just now we had given what is the simulation frequency range, what is the center frequency that we want. Optimetrics, when a parameter needs to be varied, that we need to give. That is an optional parameter only. Hence, it is showing tick mark. Since we have not given anything, that's fine. And I'll click close. So now it is ready for being simulated. So I'll click save. Now to simulate it, again right click, analyze all. You can give. Right click at the HFSS design and analyze all. Or you can also do the same over here. Analysis, right click, analyze all. Now earlier I told that we are going to perform plot of two features basically, right? So go to this results, right click, create model solution data, and select rectangular plot. I repeat, right click at the results, create model solution data, and select rectangular plot. By default, it will show S parameter S11 in dB scale. We'll leave it as such. So complete frequency range will be selected as the x-axis. Y-axis will be S11 in dB scale. So I'll click new report and I'll click close. So this is the, while running, it has just plotted the S11 over here, right? So okay, simulation is done. So it has simulated for this whatever design that we had considered. Now we wanted our design to work at 15 gigahertz. In the start, we have seen, right? Our design was 15 gigahertz. So length was approximately 10 mm. We had selected, right? The length of the dipole antenna as 10 mm. Now what we are looking at over here is with that approximate value when we simulated, we are getting a resonance. So this point is basically a resonance, and in general, we take the bandwidth operational band as where we have minus 10 dB point. So how to get it is, so right click, marker, add Y marker. We'll add one Y marker over here. Select this Y marker. In the properties, you'll be able to see that it is showing some default value. So you change it as minus 10 in the Y value. So at minus 10 of Y value, we are able to see that the band of 12.318 to 13.990, we are getting S11 less than minus 10 dB. Right? So this is the approximate range which has been, which can be used for this particular design. But we want our antenna to work at 15 gigahertz, especially the bottommost point should be at 15 gigahertz, right? So let me right click and create a marker and X marker right now. So I'm moving the X marker and I'm able to see that it's approximately resonating at 3.07 gigahertz, right? So at 3.07 gigahertz, I'm getting one resonance. So whatever frequency you decide, that will be your design frequency, and whatever you have got for this, for at the resonance, we are getting it as around 3.07, right? So make a note of it. We'll go to the paper, right? So over here, I'll write. So as we know, frequency is inversely proportional to wavelength, and in this case our dimension is approximately half the wavelength, right? So since there is a proportionality constant, so wavelength wherever whatever property the wavelength is, similarly our length of the antenna will also be proportional to it, right? So I'll just delete this portion. So what we can see is frequency is inversely proportional to the length, right? We'll use this for the simulation purpose. So what I have written is, see, F1 is the frequency that we have obtained for a length of 10 mm. So F1 is inversely proportional to L1. Since we have designed for 10 mm length, the frequency that we are getting is 13.07 gigahertz. For 15 gigahertz, what should be the corresponding length? 15 gigahertz will be the F2, and what should be the length? That will be L2. So you can write it as 13.07 gigahertz, right, divided by 15 gigahertz, right, equals, so L2 corresponding to 15 gigahertz upon L1 at our design of 10 mm, we got 13.07 gigahertz. So at our length L1, see at a particular length L1 which we designed, we had gotten resonant frequency of 13 gigahertz, right? So F1 I am substituting it as 13. It's inversely proportional to the length 10 mm. So, but for 15 gigahertz, what should be the length L2, right? So that we are trying to find it out. So let's open a calculator. So L2 equals 13, and gigahertz basically 10 power 9 and 10 power 9 would get cancelled out. So 13 times this, let's take L2 in mm itself. So 13 times 10, or sorry, clear it off. 13.07 times 10 divided by 15. So that turns out to be, sorry, I made a mistake over here. Let me again, that 13.07 times 10 upon 15. That gives out a length of 8.7 mm. So if we take a length corresponding to 8.7 mm, there is a high possibility that, again please note, it's again possibility, it's not, it may not give the correct uh, resonance at 15 gigahertz, but somewhere near to 15 gigahertz we will be able to get if the length is chosen as 8.7 mm, right? This is the first tuning that we are doing, right? So length we'll choose it as 8.71 and resimulate it. So let's go to the simulation. So based on our design results, so let's go to this project variables. So the length we had earlier chosen as 10 mm, so we're going to change it to 8.71 mm, right? The value has been changed, updated as 8.71 mm. Click OK. So the previous results may be deleted because of this. So we'll, with the S parameters, you can see some X marks over here, indicating that this was for the previous dimension, but the updated dimension, this antenna dimension has been updated right now. So we'll re-simulate it. So go to analysis, right click, analyze all. So previously we got a S11 corresponding to this one. So I'll just take it as a reference. So I'll take a print screen. Uh, this was the previous result. So I'll just store it over here as reference. So yeah, now the simulation has been completed and the resonant frequency has shifted to around 14.78 or 14.74 gigahertz with a minus 10 dB frequency points as 13.89 and 15.87. So this is a very good design when compared to the previous design, right? So here again we have obtained a frequency, resonant frequency that's slightly offset from 15 gigahertz. However, the 15 gigahertz lies at minus 10 dB bandwidth within the minus 10 dB band. So we can go ahead. However, if you wish, you can even further fine tune it. Take this as the 14.71. You can substitute over here instead of F1 and 8.71 as L1. And for 15 gigahertz, what should be the length? We can always try it out and see. So maybe approximately I'll change the parameter, right? So maybe if you substitute, it may come around 8.5 or 8.4, somewhere around it. So I'll just put it as 8.5 for now and click OK. So I'm changing it again and I'm analyzing, right? So however, you can always use optimetrics. So in right optimetrics, add parametric, and we can select the length value and we can give a range, like for example 8 to 8.7 at an increment of 0.1 mm. We can always give it like this and perform optimetric. So what it will do is for every such length, it will simulate and show a different S11 plot. So whichever one is, you are able to get. So when you simulate it again, analyze all parametric when you perform. At all the different lengths, it will calculate, it will compute the S11 and it will show. However, since I mean, we are almost near the solution, since because of that, I'm not performing this optometrics, I'm directly giving some value and we'll see at the length of 8.5 mm what we are getting as the S1. So here if you notice the offset, it has slightly moved further. However, it is almost close to 15 gigahertz, so I'll just leave it over here. However, if you want to again further fine tune it, you can always go ahead, go to the project and project variables, and you can give the select the respective lengths, adjust the length so that you can tune it to 15 gigahertz, right? However, this is almost very close, so I'll leave it as such. So the operating band, the frequency band is 14.249 gigahertz to 16.289 gigahertz. So in this range, this dipole antenna can work much effectively or efficiently, wherein more than 90% of the input power will be coupled to the antenna for radiation. Now, coming out, talking about radiation, we need to plot the overall radiation plot, right? 3D plot. So right click at the results, create far field report and select 3D polar plot. I repeat, right click at the results, far field reports, 3D polar plot. Click at it, it will show gain, total gain in dB. We'll have to select a dB scale and go to this families. So here you will be able to see all the frequency points what you have simulated. So right now I have selected it as the length as 8.5 mm. I have given the simulation frequency as 15 gigahertz only. So I'm clicking new report. So here you'll be able to see one apple type of image, right? To see how the antenna dipole antenna is radiating, we can go over here, go to this HFSS design. So I'll just hide this block, right? Radiating surface, right click, view, hide in active view. So we'll also hide the grid. You can go to the view option, grid settings. You can always hide the grid, right? And even the axis you can hide, right? Or axis I'll leave it as such for our reference, right? Now in this, right, with the antenna, we can always plot the field, right? Right click, plot fields, radiation field. So we have selected the gain plot what we just plotted and click apply. So here you will be able to see that this antenna is giving out radiation, something like this. Now, the scaling has been done as 0.25. However, I can always increase it, and transparency I'll give it to 0.6. Let me click apply. See, the antenna radiates almost uniformly in all the directions, all the horizontal directions. Whereas in the vertical direction, there is a null over here. That is the property of dipole antenna, that it will not radiate along the its longitudinal line, right? Meaning it will not radiate along its axis, whereas it will radiate uniformly in all the perpendicular plane, or you can call it as the xy plane. At the xy plane, it will be uniformly radiating, and this is called omnidirectional radiation pattern. So most of the antennas where we need horizontal direction, it should be propagating in all the horizontal directions. We will prefer either monopole or a dipole antenna or its variants, for its omnidirectional properties, meaning at all the directions it will be able to receive the signal from all the directions. At the same time, this as a transmitter, it will transmit the signal at all the directions in the horizontal plane. That is the property of this dipole antenna. So we can always slice this apple type of image into polar plots. So what you can do is right click at results, create far field report, and radiation pattern. Right? Create far field report and radiation pattern. So gain in dB scale. So we'll have the x-axis as theta and go to families in phi. So phi equals 0 we'll select. Basically along the xz plane we are going to uh, slice this radiation pattern and see how the radiation pattern is going to look like. New report. So at one side we are able to get like this, right? So for 8.5 mm, what is the radiation? So that you can select it over here. And for looking at the other side as well, if you want, so you can always go to this HFSS designs this radiation option. Go to the 3D, double click over here in theta from minus 180 to 180. Figure, we'll be able to get yeah, the complete slice. So basically, this 3D pattern has been sliced, right? We are slicing this, yeah, our dipole is there, right? So when we are slicing it at XZ plane, we'll be able to get a sliced apple type of image, which we are able to see over here. Now, if you slice it horizontally, for that how to get it is, again, right click, create far field reports, radiation pattern. A primary sweep, we will select it as phi, and XY plane is defined as theta equals 90 degrees. So theta 90 is nothing but XY plane, right? So our length of interest is 8.5 gigahertz, so 8.5 mm, frequency is 15 gigahertz. So see here, x-axis, I mean the complete angular axis, it's going to be phi right now. Basically, all the values of phi equal to 0, 1, 2 like that till 360 degrees. But at theta equal to 90 degree plane. So when you click new report, okay, sorry, uh, did I select something wrong? Oh, okay. The Y range is very, wait. I'll click the minimum scale to be 0 so that you'll be able to see this apply and click OK. So it will be near circle, right? Almost circle. So what previously we were seeing is 2.3 to 2.4 small deviation only was assigned to the radial points. However, from 0 to 2.5 when you assign, so we'll be able to see almost a circular pattern over here. And we see from the top, right? When we are slicing it at XY plane, we'll be able to see just a circle as the radiation pattern. So that's what is available over here. and this was along the XY plane, XZ plane, basically a vertical slice of the radiation pattern. So this is the total 3D radiation pattern that we had obtained, and this is the S parameter, basically our you know return loss. And yeah, I'll stop right here. Thank you. So you can design whatever is your center frequency. You can design it with based on the PPT, the slides that we had shared, and obtain your own S parameter results. So I'll take a screenshot of this and attach it over here for comparison. Right. So previously we had at first we obtained a center frequency as 13.071 gigahertz with a length of 10 mm, which was our initial length. Then we changed the length to 8.71 and further to 8.5 to obtain the S parameter or S11 close to 15 gigahertz. This S11 dip was close to 15 gigahertz, and this is the F2 minus F1. Right. Please note this F1 F2 is for reference only, but with respect to the bandwidth, if you take this F2 and F1 are basically the minus 10 dB frequency points in the S11. So this and this represents F2 and F1. So the difference of this will give you the bandwidth. Percentage bandwidth is this bandwidth upon the center frequency will give us the percentage bandwidth. You can always calculate it, right? Okay. Yeah. Thank you.